So very good afternoon. So it is unit number 2 is current control device. We have started with the BJT. So in BJT we have seen that it is an current control device. Why we say current control? Current control is turning on is done by injection of electron from external. Okay. Again there are two types. One is called NPN. Another one is called PNP. Okay, so in PNP the center layer is N. So for N the minority charge carriers are holes. So you have to somehow inject holes inside your region and try to turn on. The word bipolar there, bipolar junction transistor is there are two types of charge carriers are possible. So okay, one is with respect to NPN, another one is with respect to PNP. So turning on of the device is done by two type of the charge carriers available, either positive or negative. Okay, if it is PNP, then the center layer is N, where the minority charge carriers are holes. See, if center region is N, then what is the minority of that N? A minority of the N is holes. So you have to, by some means, you have to inject these holes, and when you inject this hole, already you have on the both side of this N-type material you have holes. So now there are free space where the electron can come and sit and jump. Okay, so if you supply excess of this holes into that N region, then the electron can move from your top to bottom. Okay, so between emitter to collector there is flow can be possible. And in another type of configuration you have center region is P type, the type of configuration is NPN. So in this case the center region is, you are having it as P. So for the minority of P type semiconductor is N. So by some means you have to inject electrons. Okay, so when you inject electron, the other two layers are already of N type, so which means they will have excess of electron, and now this electron also is there, so there is device will get turned on, and the only thing is it is being brought to conduction by the minority charge carriers. Okay, so that is the thing you have to remember. So in BJT the charge carriers are from minority charge carriers, so turning off becomes a problem. So turning off becomes the problem is the device will get turned off only if all the minorities are removed from that particular region. So if you have to remove till the last drop in your center region, the center region, if you take it as PNP and the center layer is N, where the minority is P, so all the excess holes has to be brought out. Till that the device will be in on. Okay, so that is the case. And the topic which we have not seen is negative temperature coefficient and secondary breakdown. So let us today discuss about this negative temperature coefficient and secondary breakdown. So negative temperature coefficient is nothing but for increase in temperature, the effect which is taking place is in reverse direction, or there is a negative effect for change in temperature. So if the temperature increases, what happens is the resistance falls down, or decrease in electric resistance. So if temperature increases, obviously what will happen is the number of electron that can enter your device will increase. You have to remember that. See, all the semiconductors are used as a device. So electron from externally enters the device and try to leave, and this semiconductor is only used like a switch. Okay, either you turn on or turn off. So you will allow the electrons to flow, or you will put a restriction to it. So now since all semiconductor materials are all have negative temperature coefficient, so whether this is positive thing or negative thing, if you see in a conductor, if the resistance fall, there won't be any issue, because there is always conduction band and valence band are overlapped in conductors. So if resistance fall, there is nothing. Whereas when you take as a semiconductor, he is not purely a conductor, or he is not purely an insulator. So in semiconductor, if suddenly resistance falls, what happens is current increases. This increase in current or the more number of electrons is passing a small area, so obviously there is a risk for failure of the device, or the complete device will burn. Okay, so the lower the coefficient, greater the decrease in electrical resistance for a given temperature increase. So all semiconductor device, you have to take care that it does not get eaten up. Okay, so that is why even in your system you have a processor which is made up of semiconductor material, where this semiconductor material made processor you keep heat sink, then you keep your fan arrangement. So by some means I have to remove that heat from this particular fellow. I should not allow the heat to rise the temperature. See, the temperature itself is rising because of there is injection of electron, because when an electron flow inside a semiconductor material, it will not be as free as it is moving inside a conductor. So it will hit there and here inside the semiconductors, so it will try to raise the temperature, and if this temperature is rising, again the resistance will fall. So this becomes a chain reaction. Due to one thing, another thing is happening. Because of the flow of electron itself, the temperature rises, and if the temperature rises, again resistance will fall. So this leads to entire burn of your semiconductor devices. So that is why we say we try to keep heat sink, cooling fan and all, so that to protect your semiconductor device. Then there is two types of breakdown. One is called primary breakdown, another one is called secondary breakdown. Okay, primary breakdown, we all know the primary breakdown is due to avalanche breakdown. The avalanche breakdown is nothing but you go on increase your voltage at a particular value. When voltage withstandable capability of that particular fellow goes beyond a particular value, then it get collapsed. Always we used to say, we used to compare the flow of electron with the flow of water. Okay, so when you store water in dam, it can be used whenever there is a need. Okay, but unfortunately if you go on increasing the amount of water, which is nothing but you are increasing the potential, now beyond a particular potential your dam will be unable to withstand the potential energy of the water, then the dam gets collapsed. Okay, when the water is not flowing, you would say it has potential. When water starts to flow, you say kinetic energy. Same case for electron also. So when you will have more number of electrons, when you have more number of potential. Okay, only if there is water you can open from dam. Okay, so when current possibility for current flow is available of potential difference. So when you go on increasing your potential difference between the two ends, let us assume in BJT one is emitter, another one is collector. So between the collector to emitter, if you are increasing the voltage, and if you are go on increasing, at one stage what will happen, this voltage is very high potential. This high potential is capable of damaging the entire device, and the entire device will collapse and fail. So when you do your project, you should know what is the operating voltage. Okay, between what potential you are going to place your device. So if you take a BJT, then you have to go for data sheet and see what is the primary breakdown. So if the primary breakdown of that particular device, if it is been recorded as, say, let us assume 400 volts, then you should not go for operating greater than 400. In that case, what will happen? You don't know, the device is not collapsed because of your pulse or any other thing. It is breakdown because of over voltage. Okay, so that is what we have to say. Now because nowadays we are going till 2000 volts also, or 1200. Voltage level is little bit high when compared to early days or your other way of in usual days. Usual day only 230. Now 230 has become you are going on increasing. Even we have gone till 600 kV also. 600 kV lines is there. So very high voltage, where if you use in that particular, you have to properly go with the data sheet and try to identify. So this is called primary breakdown. Whereas there is one more breakdown which is occurring, which is called secondary breakdown. This secondary breakdown is because of the process which I have explained, due to the negative temperature coefficient. Only because of negative temperature coefficient in semiconductors, there is one more breakdown called secondary breakdown. So what is happening is, I have told you have a very high potential is there, then you turn on your device. Once you turn on the device, current starts to flow. and this current is flowing inside the semiconductor is not as same as current flowing inside the conductor. In conductor, electron can freely flow, whereas in case of semiconductors, electrons cannot freely flow. There will be some obstruction in it, even though it is in on condition. Okay, that is what you have to remember. When you take conductor, when it is in conduction, there won't be any opposition. Okay, whereas in semiconductor there is opposition. So this opposition will try to increase temperature. So if this temperature increases, by nature itself semiconductors has negative temperature coefficient. So increase in temperature will increase, it will decrease the resistance and increase the electron flow. So if this electron flow is increasing, this increase in electron flow is not because of potential. Okay, not because of potential. Because of potential there is increase in current flow and try to break down the device, that is primary breakdown. Whereas in secondary breakdown, the electron flow increases, but this electron flow increases is not based on potential, it is based on the property of negative temperature coefficient. So there, since the temperature increases, resistance of the semiconductor fall, thereby it increases the current flow inside the device. Inside the device is from emitter to collector. So what happened now? So it leads to a breakdown, and this breakdown we call it as secondary breakdown. So this can be visualized from your safe operating graph. So what is this graph is, x-axis I am telling about voltage, and on y-axis I am telling about current. So for, if you take a transistor, say let us say, what you infer from this is a transistor which we brought from shop, that is BDV67C. So this is the name of that particular transistor which I have brought from shop. Now this transistor can be used with a voltage of, say let us say 100, where the current flowing across the device should not cross 0.4. So if your load draws a current of 0.4 amps, then the maximum voltage that can be applied across, applied is only 100 volts. So if you increase beyond 100, what happens is, then there is a chance for secondary breakdown taking place, and this secondary breakdown, this is the secondary breakdown, and this is called primary breakdown. So for a device there is two types of breakdown occurring. So this way you have to identify only from the data sheet. So take the data sheet and come to a conclusion that this transistor can be operated safely. If you want more current, then you have to reduce your voltage, which means current is normally what current? This current is your load current. Load current purely depends upon load. Now the current what I have drawn here, IC, please remember the IC is nothing but load current. Load current is current which is flowing across your emitter to collector to your load. Okay, so if you design, say let us assume you are designing a battery charging circuit where AC you will convert it into DC. For conversion of this AC to DC you use 4 transistors, and if that transistor is being turned on, then that current flowing is the current drawn by the rectifier or the battery charger. Are you able to understand? See, only load decides the current. If you put for mobile is drawing the current. There is nothing like so. So this current is purely depends upon load. So let us assume I have connected 10 mobiles. So each mobile draws a current of 2 amps. 10 into 2 is 20 amps. If 20 is not here, let us assume you are using a battery of your mobile draws 1 amp, and if you use 5 mobiles to get charged, then you require a current of around 5 amps. In that case, see, the voltage given to your circuit should be within this range. If you go beyond this range, that is when the voltage is 50, 60 or 70. This is nothing but input voltage. Obviously, input will be around 230 volt. In that case, this device fails. Then you should know that the device is failed because of breakdown occurring inside the device. Okay, so you have to properly select. So I repeat, this current is load current. So for this load only you are designing some circuit. So the designed circuit current you have to see. and in that current it should be within the limit of the voltage operation. If the voltage operation is not within the limit, then automatically it will break. Okay, so primary breakdown, there your current rating is more, and secondary breakdown your current level reduces. So that is what we say. So why this decrease in current? Because the current flow increases due to resistance, and due to decrease in resistance, more current, so device will break. So I cannot operate in this region and all. So drastically it will come down. So this drastic come down is because of negative temperature coefficient. So even you can see the graph, it is drawn downwards. So it is negative temperature coefficient. Okay, now let us move on to SCR. SCR is silicon controlled rectifier. So see, the entire devices itself, they go by trial and error. So first they did diode, then two diodes they connected back to back and see what is happening. That becomes a transistor. Then when two transistors they try to connect back to back, they got SCR. Okay, so it is a 4-layer semiconductor device. There is alternate P and N. Okay, you will have P, N, P, N, like that it will have, and totally you have 4 layers. The word thyristor is nothing but combination of thyratron and transistor. So that is why it is been given as thyristor. There is two state. One is either you can on or off. Okay, nowadays after you should have a clear idea that all electron devices or all circuit devices which we see is only used for switch. Here you are not supposed to talk about amplifier and all. So our motive is only to talk about either you will turn on or turn off. Okay, so it was initially tested in lab in General Electric in 1957, and there are only 3 terminals. The operating range is from 1200 volts to 1500 amps. So very high operating range is possible in case of SCR. Switching frequency is also moderate. Not so, we cannot say it is in order of mega, it is only in order of kilo. No problem that SCR will not be used in DC circuit, only in AC circuit. That also it will be used only as a rectifier. So when you use only as a rectifier, you will use it for line frequency. So line frequency is nothing but 50 Hz. So that is within our limit. So no problem. So you don't want to worry about more than 20 kilohertz and all. There is 4 states. One is called reverse blocking, then reverse conduction, forward blocking, and forward conduction. I will say what is all that 4 is. Now the symbol I have told you, connecting two back-to-back transistor. So I am connecting in a fashion such that this N and this N get merged, and this P and this P get merged. So even we will say as 2 transistor analogy. So you can see here. So one output is being taken as input for another fellow, and similarly this output is taken as an input. So it forms a loop. So when compared to transistor, the advantage what we obtained in SCR is only if you lightly trigger, that is more than sufficient. You don't want to trigger more, because light trigger itself will try to move to this, and output is being again brought in, and this is in circulating in fashion such that the triggering gets amplified. So that is the advantage with respect to our previous case, and this is the symbol of SCR. Okay, so I repeat, it is a 2 transistor analogy, which means 2 transistors are connected back to back. So configuration is as follows. The second layer is connected to the first layer, and the third layer is connected to the second layer. You can have a doubt, sir, can I do this in our lab? If 2 transistors I am bringing and combining with in a breadboard, will I get SCR? No, sure, you will not get, because all this should be done internally, and this connection should be done with silver wire or gold wire. Normal thing is not possible. Cut ஆயிடுச்சாங்க. ஓகே, நான் பார்க்குறேங்க, செக் பண்ணுறேன். இப்போ தான் போச்சா இல்லை ஸ்டார்டிங்லேயே போயிடுச்சா? ஆமாங்க, இங்கே கேட்காதுங்க, அதுக்கு தான். சரி, ஓகேங்க, நான் அதை திருப்பி உள்ளே வரேன். So I think now you can see my screen as well as my voice. Can you hear me?
Yes, sir.
Okay. If there is any issue, you just give me a call so that I will come back. Okay. So till what you are able to listen, till SCR, till what you are able to listen?
SCR, sir.
Okay, SCR starting. Okay. So what I have told is SCR is an 4-layer device. So then you are using this only for turn on and turn off, and it was developed in 1957. There are 3 terminals. The rating of SCR is little bit high compared to your transistor. Okay, so it has been operated in the range of 1 kilohertz to 20 kilohertz. When you see the diagram of SCR, it is like 2 transistors connected back to back. So the 2 transistor is the N of the first transistor is being connected to the N, where that is second layer is connected to the first layer, and third layer is connected to the first layer of the next transistor configuration. But actually speaking, in lab you cannot do this because that is not possible. In lab, when you connect 2 transistors, that will not become like an SCR because you have to do all this with the gold wiring. Okay, normal wiring is not possible. Okay, then this is the symbol of SCR. Now let us move on to the construction. So when you see the construction, here the thing you have to notice, already you have N region here. This N region we will try to increase the doping level. This is highly doped and this is lightly doped. This lightly doped region, when you decrease your doping level, the operating voltage will increase. Okay, only thing that you have to remember. Okay, a previous case and all, we introduced one more additional N minus. Here we will not introduce additional N minus and all. This N itself, when you want to prepare SCR for high voltage, automatically they will reduce the doping level of this T. So at the time of manufacturing, so that is the thing here. So here there is no additional N minus and all here. Okay, only the N region doping level they will vary at the construction itself. So you can see here the amount of doping and the thickness. So when you see the thickness of this p-type, and this is around 30 to 50 microns, and this is 50 to 100 microns, and this region is around 30 to 100 microns. And now how we are going to turn on your SCR is, I am giving a gate current. Once you gate current is given, this region will become electron. So you are already, this region is N minus, you have more electron, and this is a P region. This will be in a forward bias. Okay, so since this is in forward bias, we don't have any issue here. So only region where this is reverse bias, there is a barrier which is formed. Now since by injecting an electron, this barrier will get vanished. So once it gets vanished, there will be a flow between cathode to anode. So that is how the structure is. So now let us see with various point at which the character changes. The thing which you have to remember here is there is a 2 current called latching current and holding current. I have told you, see, you can see you can clearly see here. See, initially only gate is required. Once the gate is turned on, then you don't want to give any supply from here, because already what is happening, the output of first fellow is taken as input of second, and this is given as an output. Again this is get as output. So thereby this itself will take care, and this gate we don't want to give. So only to turn on gate is required. Once gate is turned on, the device will go work, and this will be brought off only if it is below the holding current. So latching current will be always more than holding current. So when you try to latch, you take some current, but to make the device come to off, even lesser current than latching current, because there is a circulating fashion which is taking place. So that will try to make the device to stay in on itself. Now we have told forward breakover voltage, which is nothing but the voltage at which the device get turned on without any gate voltage. This is the thing which you have to remember. See, if you are going on increasing your voltage and I am not giving any gate current, even if you are increasing beyond a particular value, even without the gate current itself, it will try to turn on. Okay, so that is called VBO. Then voltage current is the current which is required for the device to stay in on, and this is less than the latching current, because to latch I required a current, but to hold, since it is a circulating fashion, the structure, so it will be able to hold in less than the current of value. Then gate trigger current. What is gate trigger current is IG. So if I trigger at the lesser value of voltage itself, the device will get turned on. So here we have drawn only for IG is equal to 0. Okay, if I increase the IG gate current, then it will turn at this instant itself, and if I go on increase my gate current at very lower voltage itself, I will be able to turn on the device. So this is what I was explaining you. This is when IG is equal to 0. This is when IG increases further. So increase in current will try to decrease your voltage at which the device gets turned on. Okay. Then comes your 4 modes of operation, that is reverse blocking mode, reverse conduction mode, forward blocking mode and forward conduction mode. This alone you listen. So with that even we can wind up today. So the thing very useful, this 4. Reverse blocking mode, and there is reverse conduction mode. In reverse blocking mode, the device is ready to block, but you have not given anything, which is thyristor in open circuit. Okay, the entire thyristor is open, but see here reverse conduction mode, thyristor is closed circuit. So you can make the device on, or the device is there but you are not allowing. For example, for this best example is a rectifier circuit where you will use 4 thyristor. When you turn on 2 thyristor in positive half cycle, there are 2 more thyristor in which one thyristor on the top leg can be turned on, but you are not giving this pulse. So that is the condition of both this reverse blocking and forward blocking. Okay, so even with this we will stop today. Next class I will explain one by one what is about reverse blocking, what is about forward blocking, then what is about reverse conduction and forward conduction. Okay, so let us stop with this today, then we will continue.